Hi, my name is Tsachi, and in this talk I'm going to explain how flash attention works. Flash attention is a popular implementation technique for the attention head of a transformer architecture. It is designed to improve performance, and in this talk I'm going to explain how it works and how performance uplift is achieved. So in order to understand how flash attention is improving performance, we need to fuse insights from three domains. The first domain is the softmax operator. Softmax operator is a popular operator in deep learning frameworks, and we'll have to fully understand how it's constructed in order to understand how we get to improve performance through flash attention implementation. The second thing we need to understand is computer memory hierarchies and how they work. And the third insight is the attention block and how the softmax operator integrates inside it. So let's start with the softmax operator. The softmax operator is an operator that is applied on a series of numbers, finite, and it emits another series of numbers which is normalized, and it's of the exact same element count. All right, so in order to evaluate softmax, we need to do three passes on the data. On the first stage, we need to generate the maximum element of the series. So this max operation can be implemented naively serially. On high-end implementations, it is usually implemented in some parallel manner to improve performance. But at the end of the day, we have a series of numbers and we need to find the largest element. In this case, the maximum value is 9. Next, we need to generate a normalized sum of the values. This normalized sum is achieved by taking all the elements, subtracting the maximum that we found in the first stage, and then raising exponent to that result. After we have raised exponent to that result, we need to sum all the resulting exponents, and this is our normalized sum. In this case, 1.58. Next, we need to divide exponent by the elements minus the max by the normalized sum that we generated in stage 2. Now note that on the third stage, on the second stage, we need to calculate the same expression, which is exponent to the power of the element minus the max. And exponent evaluation is somewhat expensive. So most implementation usually calculate this exponent expression per element only once in the second stage, and then keep it for the third, or save it to memory and then load it for memory for the third stage for the normalization. All right, so we have a normalized series of numbers. One observation we need to do about softmax is that we actually need to read the input from memory 3 times. Once to do the max, second time to do the sum, and third time to do the normalization itself. What the flash attention implementation is aiming at optimizing is the number of reads from global memory. Those reads can be very expensive, and if we can reduce those reads, we can improve performance, and this is exactly what flash attention implementation is trying to do. So how is it doing it? In order to understand how it's doing it, we first need to understand um, the structure of any memory hierarchy in compute systems. Those compute systems can be CPU or GPU. The governing rule is the closer the memory bank is to the processor, the smaller it is and higher bandwidth it is. Okay, so if we look at a GPU compute system, in this case we have H100 specifics. Then the closest memory to the processor is the register file, and the size of the register file is 256 kilobytes per streaming multiprocessor, but the aggregate bandwidth of all the register files in the GPU is about 40 to 50 terabytes per second. So a relatively short bank, small bank, or many small banks, but very high bandwidth. The next bank is the L2 cache. And the L2 cache is much larger, it's 50 megabytes in size, but we have roughly 1/10 of the bandwidth, 5.5 terabytes per second. So when we do the math, we need to bear in mind that reading 1 byte from L2 costs as much as reading 10 bytes from the register file. So when we do the analysis, we can kind of can regard reading from the register file as a free operation, cost-free operation. And the last bank is the HBM. This is high bandwidth memory. It is off-chip memory. It is 3 orders of magnitude larger than the L2 cache. It's 80 gigabytes as opposed to 50 megabytes. But in aggregate, it has only half of the bandwidth we get from L2 cache. Okay. So how do we optimize softmax in the context of flash attention? So first, one observation. If the set of numbers that we are trying to normalize fit inside the register file, then we don't need flash attention. We can just run softmax as is with no tricks, and it would run just as fine, right? The first time when we do the max, we read it from global memory and cache it in the register file. And then for stage 2 and stage 3, the normalized sum generation and the normalization itself, we read it from register file, and there's no problem. The problem starts when the series is too large, and it can be very large. It can be, in large language models, it can be 100,000 elements, 200,000 elements, which don't fit in the register file. And in this case, and we are not, and in production, we are not doing it only on one series at once. We are usually doing it on thousands of series in parallel. That is why it fits very nicely to GPUs. So we will be dividing the series into tiles that do fit inside the register file. In this case, we are tiling our series to 2 subtiles, A and B, that do fit inside the register file. So what we'll do is we load tile A into the register file, and we are doing max only on A, and then we are doing normalized sum into A. And what we also do is per element, because we need to evaluate exponent for the normalized sum, we will keep the exponent per element, write it back to memory because we don't want to evaluate exponent again, but it will be an exponent with the local max subtracted and not the global max, and we will fix it later. Okay, so we do it for A and then we do it for B. When we are done, we have the locally normalized sum of A, the locally normalized sum of B, and the local max of A, the local max of B. That's all we have. Of course, we'll need to fix it up later because we need global softmax, not local softmax. All right, so once we have the maximum of A over B, we do max between them, and we have the global max. If we have more tiles, we'll just run a longer max operation. But because it's one scalar per tile, this calculation is very quick, and we can omit it from our complexity calculation. Next, we need to have the global normalized sum of A and B, and for that we need to fix up the partially generated normalized sum of A and B. So this is our partial normalized sum, right? And what this sum is calculated, it's calculated with the maximum of A, and we need it calculated with the global maximum, not the local maximum. So we generate this scalar per tile, which is e to the power of x max minus the global max. And we multiply by it. So it's one multiplication operation per tile. And those two elements cancel each other out. And we got our partial global normalized sum. And then we do it for each tile. We sum up all the partial sums and we have a correct evaluation of our normalized sum. Great. Now we perform stage 3. So with stage 3, we come up with this expression. And again, it's one scalar per tile. Okay, so it's e to the power of x local max minus the x max divided by the sum, the global normalized sum that we just calculated. We multiply it by the elements that we kept, so e to the power of x minus the local max, and we have our correct normalized value of softmax. So now let's try to do just a tally on how much IO did we do, right? So for stage 1, right, we read a tile. We had to read it from global memory to do the max, all right? Then on stage 2, we did our local normalized sum plus per element exponent, but that was a second read from the register file. So for all intents and purposes, that read is free. All right. Then we generated the global max and the global normalized sum, and those are one scalar per tile. So from complexity consideration, we can remove them. They are not very meaningful. And then on stage 3, we had to reread the entire series for this one multiplication operation, which does the fix-up and the normalization, and that's a second read from global memory. So what we principally did is we reduced 3 reads from global memory when implemented naively into 2 reads from global memory when we are doing softmax. And that's nice, that improves performance, but what we'll see shortly that when it comes in the context of flash attention, we can actually do this without adding any additional IO to the system. So first, let's review how attention block looks like. So I kind of put a decode, typical sizes for the decode stage. Okay, so we have the QKT matrices where we need to Q matrix and the K transpose matrix, which we need to multiply. The common dimension is the head dimension, which is relatively small. It's 128 elements or 256 elements. The length of the K matrix is the length of the context, which can be very long. In this example, I've put 18K, but it can be 100,000 Ks or 200,000 Ks elements. And we do the matrix multiplication. We have the QKT matrix. Usually we multiply by the square root of the head dimension, but in this case we will skip that. And we apply softmax on that matrix, right, row-wise. Okay, then we have to multiply that matrix by the V down matrix, which gives us the result, and then again by the V up matrix, which returns us to the embedding space. So this is how the attention blocks looks like. And now if we implement the attention block naively, right, let's see how much IO we have. Okay, so we generate the QK transposed matrix. This is like one write of the matrix. Then if we have 3 softmax reads, then we read it 3 times. We write the result of the softmax once. Then we read this tensor again for the second gem. So overall, at a minimum, we will be reading and writing the QKT matrix 6 times. Okay. Now let's try to reduce that. So with flash attention implementation, what we'll do is we will fuse the first 2 passes of softmax when writing out the matrix of the first gem. So we will do the gem, the matrix multiplication operation. Then we'll do the first and the second stages of softmax, generate the local maxes and the local normalized sum, and do the exponent, and then we'll write out the values when they're already raised by the exponent. And then when we read the tile for the multiplication by v, okay, we can do the third stage of softmax and do the second gem, which is the multiplication by v down. And what we principally did is we reduced 6 IO operations naively into just 2. And this is where the big performance comes from. So thank you very much for listening. The animation in this tutorial were made using the Manim library, and the animations were coded using Poolside's Laguna coding agent, which will become open source very shortly. So feel free to experiment with it. Thank you.